Hello, my name is Abby Faber, and today I will be teaching you about methane and its role in climate change. First, I will talk about how methane is synthesized. In 1897, a French chemist named Paul Sabatier discovered that in the presence of a nickel catalyst pressure and at high temperature, carbon dioxide and hydrogen react to produce methane and water. This is called the Sabatier process or the Sabatier reaction. Nickel is the most widely used catalyst because it's the cheapest, but ruthenium and rhodium can also be used. Next, the structure of methane and its properties. Methane is made up of one carbon and four hydrogens. The bond between each hydrogen and the carbon is a center of high electron density. Each bond repels the others, and the hydrogens move as far away from each other as possible, which makes the optimal bonding angle between the hydrogens 109.5 degrees and gives it a tetrahedral structure. Since there are no permanent electron density dispersions in the molecule, and therefore it isn't polar and it doesn't have any charges, the only interactions that can occur between molecules are London dispersion forces, which occur when the electrons of the molecule randomly disperse to one side of the molecule and create an instantaneous dipole, which has a partial positive and a partial negative charge. The instantaneous dipole induces a dipole, and the partially negative side of one molecule is attracted to the partially positive side of another molecule through electrostatic interactions. The attraction between the two molecules is called the London dispersion force, or the LDF. The LDF can be easily broken because it isn't a strong interaction. As soon as you heat up a substance with LDFs, the electrons will start moving more and dispersing around the molecule, changing the partial charges of the molecule and breaking LDFs. A solid would have the most LDFs, a liquid has some, and a gas has a very little amount. Since the only interactions between methane molecules are LDFs, and they aren't very strong, methane has a very low melting point and boiling point, which means it usually exists as a gas. The bonds between the atoms in methane are sigma bonds, which allows the atoms to rotate and vibrate. The types of vibrations a molecule can have are symmetrical stretching, asymmetrical stretching, scissoring or bending, rocking, wagging, and twisting. Methane undergoes symmetrical and asymmetrical stretching. The different energies of vibrations in molecules are quantized and can be measured through infrared or IR spectroscopy. IR spectroscopy measures the energy of the vibrations in a molecule and the absorption of IR radiation. The picture on this slide is an IR spectrum. On the right side is the fingerprint region. You don't assign any of the pinks to specific bonds in this region. It is used for pattern matching. As you move to the left of the spectrum, there's a higher frequency and a higher energy. The types of bonds that show up on the left side of the spectra absorb more IR radiation and have more energy. The absorption of IR radiation depends on four things. 1. The bond strength. The energy needed to stretch a bond or make it vibrate in other ways depends on the strength of the bond. For example, multiple bonds appear at a higher frequency or energy in the IR spectra than single bonds. 2. Whether the bond is stretching or bending. It is easier to bend the molecule than to stretch a bond, so bends appear at a lower frequency. 3. Masses of atoms. Bonds to very light atoms, particularly hydrogen, appear at a higher frequency. 4. The dipole moment of the molecule must change. The dipole moment is equal to the magnitude of the charge multiplied by the distance between charges. As a molecule vibrates, there is a fluctuation in its dipole moment, which induces an electric field that interacts with the electric field associated with infrared radiation. If there's a match in frequency of the radiation and the natural vibration of the molecule, absorption occurs. Because of all these reasons, the bonds in methane have a high frequency in the IR spectra, which means it has a higher energy and can absorb more IR radiation. Since the frequency or energy of the vibration is inversely related to mass, an atom with a smaller mass would vibrate at a higher energy. So an atom bonded to a hydrogen has a stretch with a much higher energy than other atoms. Also, Methane has stretching between its bonds, not bending, so it has more energy. As you can see on this slide, the peak in methane's IR spectrum is located towards the higher energy side of the spectrum. However, since methane can absorb more IR radiation, this can make it more dangerous in the atmosphere. To explain this, we need to talk about the greenhouse effect. The greenhouse effect occurs when energy from the sun, which is infrared radiation, is absorbed at Earth's surface and reflected back into the atmosphere where it's absorbed by greenhouse gases. The greenhouse gases are carbon dioxide, methane, water vapor, and nitrous oxide. The greenhouse gases then radiate the IR radiation back to Earth's surface, to another greenhouse gas, or out to space. A lot of people focus on carbon dioxide as a greenhouse gas, but methane is just as important. According to the most recent report by the Intergovernmental Panel on Climate Change, methane has 34 times the impact of carbon dioxide, and this is because it absorbs more IR radiation in the atmosphere than carbon dioxide. This is because the carbon in carbon dioxide is bonded to two oxygen atoms, which have more mass than hydrogen. As we learned, the energy of the vibration is inversely related to mass, so the energy of the carbon-oxygen bonds would be lower than the energy of the carbon-hydrogen bonds. Therefore, methane absorbs more heat in the atmosphere. Why we need to be worried is because the amount of methane in the atmosphere has increased due to human activity, mainly from the livestock production systems involving ruminants, which produce methane through gas, essentially. Ruminants are specific kinds of mammals. Cows and sheep are examples. In America, we've increased the amount of cattle we produce dramatically, and because of that, methane emissions have increased as well. The more methane that's in the air, the warmer the earth will be because of the greenhouse effect, and the faster the climate will change. The best way to reduce methane emissions and slow down the rate of climate change is to stop producing ruminants. Unfortunately, cattle provide much of the food in America, including beef and dairy, but reducing our intake of beef and dairy can reduce the need and production of cattle, and therefore reduce methane emissions. Here are my references that I used for my research for this project. I hope you enjoyed my presentation.